Hi, welcome to Precalculus. Today's topic is graphing a polar equation in the case of a Lemniscate. Lemniscate means a ribbon in the shape of infinity or figure 8. Uh, the two cases that we are going to look at, one is built with a cosine, the other one with a sine, as you see here. So r squared is equal to a squared cosine of 2 theta, or r squared is equal to a squared sine of 2 theta. As usual, the radius of the figure is a. We have two simple cases. With the cosine, it's horizontal, as we see here, and with sine, it is at 45-degree angle, and as you see it here. Both of these have some resemblance to roses in the sense that we have a number of petals. Here the number of petals is 2. That's driven by the number that we have over there. And so the graphing of these things is going to be rather straightforward because we have very few steps to take. Let's go ahead and do a simple exercise and then come back and investigate deeper to see how the tracking of the point on the curve is going to happen. We are going to see a nice surprise here. Let's wait for that. Okay, so this is a typical question that you face. R squared is equal to 16 cosine of 2a. So that number is square of a radius. So the radius of Lemniscate is going to be 4. Cosine means it's going to be horizontal. So it's going to be very simple here that we come and say, okay, radius is 4. It has to be horizontal. And then, well, that's it. Let's see. Thankfully, we are correct. Let's try another one. Let's see if we can catch a sine. So sine, square of radius is 36. So radius has to be 6. So we adjust ourselves to radius of 6. For the case of sine, it's tilted at 45 degrees. So that is what we choose. And that's it. So, we essentially solve these problems in 2 seconds with the software that's provided. Of course, graphing it with the point plotter, that's going to take longer, and we have to make a table, and just as we did for the previous case of roses, it's going to take a little bit longer. Let's go ahead and try to do this thing in our software. Let's see how does that go. Let's see the animation of the figure. Okay, here we are on our trusty animator. We are going to look at this thing while it is developing. So first, let's go take a case of the horizontal one. I took a square root of the equation so that I can use it in my software here. And let's see, this is going to control the tracking. So as I move, let's see, you see the curve is developing. So at 0, we start at this horizontal tip. Our angle is shown by this letter theta here, so we are at the angle of pi over 6. And of course, our radius r is going to be square root of cosine of 2 theta. So if this is pi 6, double of that is pi third. Cosine of that is 1/2. Square root of that is going to be 1 over square root of 2. So we are going to be at a distance of 1.4 almost here. So that's how we are confirming we are in the correct place. So we go, you see that we have made it to 90 degrees. As soon as we pass 90 degrees, what happens? excuse me, as soon as we pass 45 degrees, what happens? 2 theta exceeds 90 degrees. So cosine of that is going to become negative. Square root of that is going to become an imaginary number. And as a result, r becomes imaginary, and we could say it does not exist or is not in our plane and such. This situation is going to continue while we are traveling. So all the way through. So notice what happened. As soon as we pass through this 3 pi over 4, double of that is going to be 3 pi over 2. So double of that has passed through this point. Cosine of that starts to become positive, and the curve starts to reappear. Now the interesting thing I promised you to show you is that this has a sharp corner at this point. So this figure 8 is not going to develop the way probably you would do it by handwriting, which is come down and go back up and draw it smoothly. Rather, it is having a sharp corner. So by now we have gone through half of the curve, and we have witnessed this sharp corner here. Now let's continue. So again, this is our theta. This theta, our cosine of a double of this angle is going to be a positive number. Therefore, we have r. Now, as soon as I pass this mark, which is 5 pi 4th, again, inside the radical is going to be negative. R becomes imaginary, and we continue for a while. There is nothing to see or draw there, and we expect that our next critical angle is going to be at minus pi over 4. So that is where the remainder of this curve starts to show. So what we see here is another sharp corner here, and then I go all the way to the end. So again, this is case of Lemniscate in with a cosine which is horizontal, and then surprise thing that we saw is that it has a sharp corner here, turns back, bounces back and goes through, and bounces back again and goes through, as opposed to probably thinking that as we go through we are just smoothly going in, perhaps turning around this way and so on. So that's not what's happening. It has a sharp corner. Okay, so that was the interesting thing. Now let's go ahead and do some other examples. So I am going to now look at the case of the sine. So the sine, let's see what happens. So at zero, I start at the origin and move up. I go and here's the furthest I'm going to make. My r is 2, so that's how far out I'm going to go. And then I turn around, and then my petal is finished. Now after this, as the angle gets larger than 90 degrees, double of that is going to be more than 180, and the sign of that becomes negative. Square root of that becomes imaginary, and that's why you see this r is imaginary here. Now we continue. So there's nothing to see for a while because r all the way through is imaginary, all the way until my angle hits pi. Double of that is 2 pi, and I am going to go into positive territory for sine. So now notice again, interesting thing, this curve came down here, and now it goes at 90 degrees and it starts to continue and then come back, and then again r becomes imaginary all the way until I finish with 2 pi stays imaginary. So we had a sharp corner on that side, another sharp corner on this side, and the curve is not smooth at that at the origin. Okay, so that was another thing to look at. Next, you might be wondering, why is it one of them horizontal and the other one is at 45 degrees? How about some other angle? Well, I can remind you of something from very beginning of this course, or perhaps your course in college algebra. You remember that if you have a function and you subtract something from its argument, the function is going to move to the right by that amount. Now, what is the equivalent thing in polar? What if I subtract something from the argument of my function? So here I'm going to take a look at Lemniscate with some number subtracted from the argument. So here is my Lemniscate. Okay, R is equal to capital R times square root of cosine of 2 theta. That's how it looks like. Now if I go subtract something from my theta, some number, I call it S. If I subtract, what do you think is going to happen? Perhaps you want to pause this thing, place your bets, and see if your bet is correct. So did you do that? Did you pause? Think what might happen? Well, what happens is that it's not the translation that we saw in Cartesian coordinate. Rather, the concept of translation here becomes a rotation. That is, as I change my S, let's mark what the S is. Let me just remove this, not helping. So changing the amount that you subtract from their theta simply causes a rotation. And you can go ahead and experiment with other things, such as, well, what happens if instead of 2 I have 3 theta, and well, you can try all sorts of things here, like looks like the roses we studied last time, is that right? At some angle. And you can imitate things looking like cardioids and other graphs that we had seen before. So polar graphs are quite interesting. We saw what? We saw circles, we saw lines at the very beginning. So we saw line, we saw circles, then we saw lemniscates, then lemniscates, and a combination of all of them. Okay, now let's go ahead and so the exercise, we showed how the exercises go in this case. This is very simple. I'm not going to tire you with point plotting. It's going to be very similar to what we had last time. Okay, until next time, good luck and God bless.